Yeah, I'm really excited to be giving this talk. Before I even get started, I do want to mention that there have been at least 5, I think I got them all, previous talks on X-ray transient absorption in this series. They're all really fantastic, so I encourage anyone who missed any of these to go back and check them out. And yeah, I also just want to thank Jerry for putting together this fantastic series. It's been a really great thing to get me and my students, and I know so many other people through 2020, so very happy to be a part of it. Today I'm going to be talking about some work that we've done using X-ray and optical transient absorption to look at some irreversible photochemistry, in particular this copper catalyzed photocycloaddition reaction. Just in general in my group, a central theme is looking at photochemical reaction mechanisms using time-resolved spectroscopies. And photochemistry, as opposed to photophysics, introduces a number of unique challenges, given the fact that we're looking typically at irreversible transformations. And so we're depleting our pool of reactant as the experiment proceeds. In our home lab, we do a lot of work looking at organic photochemistry, so looking at these reactive moieties that are attached to visible absorbing chromophores. This is homogeneous organic chemistry, and so it's not really amenable to X-ray spectroscopy without really trying hard, which we don't really feel like doing, so we exclusively think about this from an optical perspective. But we also look at a number of systems involving transition metals that allow us to do our X-ray measurements, and then of course benefit from the element specificity of these techniques. So as I said, today I'm going to be focusing on this copper catalyzed reaction, and so we do look at transition metal catalysis a lot, but we also have some examples where we're looking at the photochemistry and photophysics of transition metal species itself. So I mentioned in my abstract, and I apologize, as I was putting this together, came to the conclusion that there was no way I'd be able to put complete stories for both of these systems into this talk. So I'm only going to focus on this one. This you'll have to wait for the future. But yeah, so we do have some results for looking at the aqueous ferrate ion and seeing branching between photophysical relaxation and photochemical reduction of this upon excitation. So that's, yeah, sort of the unifying theme. The reason we're interested in this photocycloaddition reaction is because it's enormously useful as a technique for synthetic chemistry. So in 1964, pretty remarkable, almost back-to-back, a couple months apart, both E.J. Corey and Phil Eaton published what have since become very much classic syntheses, employing 2+2 photocycloadditions. In the case of E.J. Corey, doing this natural product synthesis. In the case of Phil Eaton, making his famous cubane molecule. And both of these schemes took advantage of this reaction that takes 2 alkenes and forms a cyclobutane from them, which of course is a very strained cyclic species, and so forming these cyclobutanes is often fairly challenging, but doing it with light, where you can take advantage of the enormous amount of energy in a photon, provides a pathway toward doing that and forming something as challenging as this intermediate here in the cubane synthesis. So it's been a very useful reaction for well over half a century at this point, but that's not to say there isn't plenty more work to be done. So it's very much an active field of inquiry right now. So just last year, Teshik Yoon's group showed that by using this chiral iridium photoredox catalyst, they could control and direct the enantioselectivity of this reaction. The year before, Emily Weiss's group used quantum dots as both the photosensitizer for the reaction, allowing them to do this with visible light, but also as a template that would allow them to control and even reverse the regiospecificity of this reaction compared to what you get in solution untemplated. And then also last year, Stephen Lopez's group did these massive amount of surface hopping trajectories to look at reaction intermediates and product yields from a putative cyclobutane reaction intermediate, intermediate species to form cyclobutane. So it's very much still open to inquiry in fields ranging from theoretical chemistry all the way to organic synthesis. So before I go any further, I do want to point out that there's 3 distinct routes to a 2+2 photocycloaddition. The simplest is direct photoexcitation of your substrate. So today I'm going to be talking mostly about norbornene as a substrate, this molecule here. So I'm just showing that as an example here. Norbornene is an unconjugated olefin, and so the pi to pi star transition here is very, very high energy. So you need really, really short UV to be able to excite that transition to form this excited state, but you can do it. It's possible. Formation of this excited state then leads to intersystem crossing to the triplet diradical, which persists for quite some time. And so if it encounters another molecule of itself in solution, it can lead to formation of the dimer with the cyclobutane in between. If you don't want to have to use really, really short UV, you can do this approaching the visible using a triplet photosensitizer like benzophenone that I've shown here. So you excite the benzophenone instead, and then once this forms the triplet, you'll get triplet energy transfer to your substrate, and then that can then react with another ground state molecule. But we're interested in the copper catalyzed version of this for the obvious reason that copper gives us something to look at with X-rays, but it is itself very, very useful for a number of reasons that I'll get into in a minute. It also allows you to approach something closer to the visible for unconjugated olefins like norbornene. Yeah, so it's a very, very, very useful reaction. And it was studied in depth in the 70s by Salomon, who figured out a number of things about this reaction. So he was interested in it because, like I said, it allows you to use non-conjugated alkenes and do this cycloaddition with near UV light. Furthermore, it also can greatly improve the quantum yield of this reaction for substrates with really inefficient intersystem crossing. So before I showed benzophenone as a photosensitizer, enones in general are really great. And so if you think back to the mechanisms from E.J. Corey and Phil Eaton's syntheses, they both used enones as what you're directly exciting. The reason for that is they have very high intersystem crossing yields relative to relaxation, and so you get fairly high quantum yields. But if you don't have an enone like norbornene, this can greatly improve your quantum yield. Furthermore, the copper itself serves as a template to hold these two molecules in place to direct the regiochemistry, the regioselectivity of the reaction. So all that's great, but there are a number of quirks that sort of limit its utility. So it's limited in scope to cyclic alkenes like norbornene for intermolecular cycloaddition, so formation of a dimer. And if you want to do intramolecular cycloaddition, it's limited to linear 1,6 dienes. And it's perhaps a little surprising, but 1,5, 1,7, 1,8 dienes are essentially completely unreactive, which is sort of strange, but also something that we think if we figure out mechanistically what's going on step by step in this reaction, we might be able to figure out a path toward or a path around that limitation to greatly improve the scope of this reaction. So that's sort of our goal here in this mechanistic investigation. So of course, Salomon himself did quite a bit of mechanistic work here. He didn't have the benefit of X-ray spectroscopy or X-ray transient absorption spectroscopy or even optical transient absorption spectroscopy, but based on some real-time kinetic studies, he was able to propose many possible reaction mechanisms. The one he preferred at the time was this photocupration mechanism, where you form a transient copper 0 species through a ligand to metal charge transfer. But he wasn't really able to find any conclusive evidence to pick any of these mechanisms over another. The one thing he was able to figure out definitively through these concentration-dependent kinetic studies is that the reaction proceeds exclusively through this bis-coordinated species where you have two substrates coordinated to the copper. It doesn't proceed through a singly coordinated norbornene that is then excited and then encounters a ground state norbornene in solution. That is not operative at all. And so this was really exciting to us because it meant that if we could figure out a way to prepare a sample that was exclusively this species, then we would have a nice, neat, clean starting position for doing these mechanistic investigations with transient absorption. So here I've just put up a couple of different possibilities. So in the middle, there's the photocupration mechanism going through a copper 0 from the LMCT. We also have these possibilities of going through copper 2 for following metal-to-ligand charge transfer in MLCT. We could also think about this going through a concerted mechanism. You could think about the copper as essentially just redshifting the pi to pi star transitions of the ligands, possibly, and so staying in a copper 1 oxidation state the entire time. There's also a question of whether you form whether you only go through monoradical or diradical species, metallocycle intermediate, a linear intermediate. So there's many, many unknowns, and we thought, what can we do to try to at least exclude some of these possibilities, if not figure it out definitively? So, like I said, we have to take into account the fact that we're consuming our substrate as we're performing this reaction, but this really is more or less a perfect system for X-ray transient absorption for a number of reasons. One, norbornene is cheap and it's extremely soluble in THF, and both of those things mean we can make massive samples where the norbornene is in 100-fold excess to the copper, and it's actually 200-fold excess, but since we're trying to form this bis-coordinated species, I say it's 100-fold. And so at 100-fold excess, we can imagine that the equilibrium between the bis-coordinated, monocoordinated, and uncoordinated copper is shifted almost exclusively to the bis-coordinated species. Since we can make such a huge amount of it in this huge excess, if we prepare a liter of this solution after a whole day of illumination with the laser, just counting, in terms of number of photons, we're only expected to lose about 2% of our substrate within a day. And so since this quantum yield is going to be dependent on the concentration, since it's going to shift this equilibrium, we want to make sure we're not changing the concentration of the norbornene during the course of our measurement, or else we're going to lower our quantum yield and thereby affect what we're actually measuring. We can easily prevent copper oxidation in solution by using copper metal for synproportionation with any oxidized copper 2. Of course, the element specificity of X-ray transient absorption is fantastic, but also, since we expect this reaction to have an ultra-fast component, but then a much slower component, we can take advantage of the 24 bunch mode timing structure at the APS to look at longer dynamics. So we're using a 10 kilohertz laser, and so if we're getting one laser pulse every 100 microseconds, we're getting dozens of X-ray pulses in between that give us all of these pump probe delay times for free. So we can simultaneously do a picosecond measurement and these nanosecond to microsecond measurements all at the same time. So here's our actual setup. You can see we have our flowing liquid jet of our solution that we're hitting with the laser using the third harmonic of the TISAF laser, and then catching it and recirculating our sample, which, like I said, we do for about a day at a time. This whole thing needs to be very, very rigorously enclosed so that we can keep it entirely air-free. But if we do that, we don't really see any evidence of oxidation over the course of 24 hours. And we follow that up with by comparing our laser on and laser off to get different spectra. But I think with that, that's a good time for a break if there are some questions.
Indeed, there are a few questions. I'll start with Matthew Marcus.
Yeah, I was wondering about the possibility of carbon KH spectroscopy. Of course, you'd probably have to do it at a different facility, and you'd have to have, say, a helium atmosphere or vacuum.
Yeah, yeah. The real challenge here is, you know, like I said, we really want to do these experiments under catalytically relevant conditions to make sure that we're actually looking at the reaction intermediates that form during a normal photocatalytic reaction where you just put your sample in a photoreactor. And so the challenge there is concentration, right? So even if we're, you know, to get this, to shift our equilibrium toward this species, we're at 100-fold excess of norbornene, meaning that very, very little of the actual norbornene in solution is going to be involved in the reaction. On top of all of that, even though the norbornene's in huge excess, it's also in a solvent that is, you know, several tens of molar.
Which is all carbon.
Yeah. So on the one hand, looking at the copper KH is fantastic because we have all of this excess norbornene that might be challenging for other types of measurements, but we don't care about that because we only see what's happening at the copper. But it does make the idea of doing ligand KH measurements unlikely. But we would love to. That would be fantastic.
A possibility might be to look at the copper L edge. Might be more sensitive to valence and less to other things.
Yes, yes, and I think yes, we could figure out. You know, you'd still have the challenges of attenuation that you get in soft X-rays for doing this in solution, but it certainly wouldn't be insurmountable as long as you're actually looking at the copper.
Okay, we've got another question, Yang Ha.
I just wonder what's the thermodynamics of the reaction? So which direction is energetically favored? And that may help to understand the role of the copper ion.
Yeah, so you're talking about you know, 2 norbornenes in solution versus this dimer.
Right.
Yeah, so I mean, this is definitely thermodynamically uphill because you have this strange cyclobutane. I can't give you specific numbers, but
yeah, but okay. So what is the driving force? Is it just the photon, or you have to heat up the system?
Oh yeah, so this generally. So if you think back to the mechanism where you just directly excite this is only going to occur if you, or I guess without the copper, this is only going to occur if you form the triplet diradical, because then you have unpaired electrons that can then react with the excess electrons in the alkene of another molecule of the substrate. So as soon as you form one carbon-carbon bond, now you need to form the other for that radical to relax, or for those 2 radicals to relax. With the copper, of course, it could be something completely different. And that was kind of the goal of looking at it this way. So I will touch upon that a little bit more as we kind of look at this piece by piece with the copper.
Great.
Okay, you might be having just a little bit of lag, Dugan, so I'll suggest that you mute your video to save bandwidth, and then you should continue.
All right. Let's see. Okay. So right, what do we actually see? Well, before we did the more fun experiment with the norbornene, we wanted to do a control with just the copper triplet so we could make sure that what we were seeing with norbornene was indeed photochemistry. So we did this transient absorption measurement, exciting with 267 nanometer light with a pump probe delay time of 100 picoseconds. And we, since we can estimate our excited state fraction, we can subtract our laser, a certain amount of our laser off spectrum from our laser on, and reconstruct the absorption spectrum of our excited state, which I've shown in cyan here relative to the ground state of just copper triplet in THF. And so we see a very clear difference in the 1s to 4p region of the spectrum here. So we have this fairly unresolved spectrum for the ground state that splits into at least 2 distinct peaks in the excited state. And we also see this change in relative amplitude. But as soon as we get to 153 nanoseconds, the time the next X-ray pulse arrives, we get back to what essentially looks like the ground state, except with higher amplitude of the 1s to 4p. And that doesn't change at all for the rest of our measurement window. We measured out to, in this case, 30 or 50 microseconds, and we don't see any change after 150 nanoseconds. So nothing really much is happening. So just comparing all 3 of these ground state 100 picosecond, 30 microsecond here to highlight those differences, we see this difference in the 1s to 4p between 100 picoseconds and 30 microseconds. But in both cases, we have overall higher amplitude than we do in the ground state. And importantly, in all cases, we don't see, if you take the first derivative of this, we don't see any evidence of an edge shift, and we also don't see any evidence of a formation of a pre-edge. So it doesn't appear that we're doing any type of a charge transfer, be it an LMCT or an MLCT, here to form copper 2 or copper 0. It appears that we're staying as copper 1. But what's actually happening in the 1s to 4p? So here I'm just showing the different spectra that we acquired, so laser on versus laser off at these various times. You see this very strong bleaching, or this very sharp bleaching feature that gives you the splitting of the 2 peaks here, and that essentially decays by the time the next X-ray pulse arrives. So where does this come from? Well, we went back to Ed Solomon's work from the 80s, and through the analysis of the spectra of many different copper complexes, he showed for comparing a number of different 2, 3, and 4 coordinate species that in all cases where you lose coordination, so loss of a ligand or decrease in covalency, you get this increase in absorption on the redder side of the 1s to 4p, followed by a little bit of bleaching around the edge. And so that looks more or less exactly like what we're seeing as early as 150 nanoseconds and 4 microseconds. And so what we're seeing is totally consistent with what we'd expect for photodissociation of a ligand, which perhaps isn't too surprising. And so to summarize what we concluded for copper triplet only in solution, we don't really see any evidence of a charge transfer state at 100 picoseconds or anywhere after that. The spectrum doesn't change at all after 150 nanoseconds. And at all times that we looked at, the XANES spectra were consistent with loss of a ligand. We had hoped to confirm this with XAFs, but our XAF signal was very weak, so it wasn't really very conclusive. Yeah, so overall, we concluded that upon photoexcitation, we're doing a photodissociation of a solvating THF molecule by exciting an N to 3s transition that's mostly oxygen, located on the oxygen of a THF molecule. Now, with that done, we could add norbornene and see what's different. And immediately we see what shows all the hallmarks of copper 2 spectrum. So we see the appearance of this pre-edge feature here. So just a reminder, copper 1 is a D10 metal, copper 2 is D9. So you would expect to see a pre-edge here. We also see an edge shift of about 1.5 electron volts, consistent with photoinduced oxidation to copper 2. So it definitely appears that at least by 100 picoseconds following photoexcitation, we're in a copper 2 transient state. That's not to say that we're necessarily directly populating that state. We can't tell, but at least within 100 picoseconds, we're in a transient copper 2 state. By 150 nanoseconds, all of that has gone away. The pre-edge is gone, the edge shift is gone. The spectrum looks almost superimposable with our ground state spectrum, except of course a lot noisier. But it doesn't stop there like we saw with copper only. It continues to evolve on the hundreds of nanosecond to microsecond time scale. And how it evolves is through the increased absorption in the 1s to 4p regions. And so again, this is consistent with either loss of ligand or decrease in metal-ligand covalency. And so we think, you know, this would be consistent with formation of the product, because of course formation of the cyclobutane means you no longer have olefins to coordinate to copper, and so the product would dissociate off, and you'd expect these 1s-4p peaks to get larger. So we think that that's happening here on the microsecond time scale. So again, comparing our 3 different spectra, and then from this we can assign this spectrum to our transient copper 2 state, it's our MLCT state that I'm going to call a triplet, just because it's at 100 picoseconds, and we have more evidence for that from optical transient absorption. And then at 30 microseconds, we see the copper following what we think is after dissociation of the norbornene dimer. Now, comparing this to the copper only, I really just want to stress, you know, the difference between this feature here, which is a true pre-edge in the 1s to 3D sense of a pre-edge, versus this feature in the copper only, which is a 1s to 4p. So there are very different energies, despite the edges being at the same energy. As you can see here, we also don't see the edge shift in the copper only, and so that's why we say that we don't see any evidence of charge transfer with just copper, but we do with copper and norbornene. So to add to our running summary for the copper plus norbornene system, we can see that the XANES shows clear signature of a copper 2 species at 100 picoseconds, but we get reverse electron transfer to go back to the copper 1 species within 150 nanoseconds. However, something is still happening. We're not just relaxing back down to the ground state, because that spectrum continues to evolve, and we see something that would be consistent with ligand loss that happens at times beyond 300 nanoseconds. And so we think we're forming a copper 1 intermediate following reverse electron transfer from the copper 2 excited state on the 100 nanosecond time scale, but we couldn't really nail it down any more concretely than that. We did do some kinetic, we tried to acquire some kinetic traces to figure out what that time scale would be, but given the limitations of our beam time, we only measured out to about 2 nanoseconds for our 2 systems. So for copper only, we looked at that sharp bleach feature, and we saw that it disappears with a time constant of about 300 picoseconds, and then stays more or less consistent after that. The copper and norbornene, we see that bleaching appear and then not really change at all over 2 nanoseconds. So yeah, we had sort of this gap in knowledge where we knew that it persisted for at least 2 nanoseconds, but shorter than 150 nanoseconds, and we didn't really know what in between. We then took advantage of the full pulse timing structure, as I alluded to at the beginning, to try to look at the microsecond dynamics. And so this is just you know, looking at our X-ray spectrum versus time, where each of these time points is 150 nanoseconds apart as our X-ray pulses arrive. So you can see that following the arrival of the laser pulse, it doesn't look like too much is happening in these spectra, but you can see some curvature in the shape of these features within the first 10 microseconds or so. And so we wanted to look at that in a little more detail. And so here I'm just showing, if we look at the kinetics, the microsecond kinetics from that sharp bleach versus, this is just an example. I picked this feature here because it's fairly strong, but it's, we see the same sort of behavior anywhere else we look in the spectrum. If we look at the sharp bleach, that bleach is so far down, it would be off the slide, so I cut it off. It recovers by the arrival of the next X-ray pulse. We saw from the kinetics traces that it recovers within 300 picoseconds. But then we see this slow rise of the excited state absorption there that appears to occur on the microsecond time scale, versus everywhere else in the spectrum, we see an instantaneous jump with the arrival of the laser pulse, and then it's essentially flat. This is very, very different from what we saw with copper and norbornene, where we see that slow rise that's almost superimposable with what we see only in that one energy with the copper only. And that appears basically anywhere we look in the different spectrum that we have signal. We see this slow rise. And so to get a better idea of what that time scale actually was, we subtracted the blue from the red to look at the difference between the two and fit that to a 5 microsecond time constant, suggesting that there are some ligand dynamics happening on the 5 microsecond time scale. Now, the one other thing that we measured at the time was a different substrate. Instead of norbornene, we looked at cyclohexene. So this just differs from the fact that it's not a bicyclic compound. It doesn't have that additional bridging methylene group that norbornene has. And so we didn't expect to see too much different. And instead, we were shocked to find that our signals were radically different. So we saw the same sharp bleaching of in the 1s-4p at 8.98 at 100 picoseconds with cyclohexene, and that disappeared within the next X-ray pulse. But if we average together a handful of X-ray pulses to get something like microsecond time bins, we can get a good enough signal to noise to actually look at our spectra. And what we see is the same shape spectrum. So it doesn't appear that the spectrum is really changing shape at all over the course of several tens of microseconds. It does appear to be slowly decaying on the tens of microseconds time scale, but it doesn't appear to be changing shape. And even more remarkably, its shape is entirely different from what we saw for either copper alone or copper norbornene. Remember, for both of those, we saw something consistent with loss of a ligand, where we see excited absorption in the 1s-4p region. Here we see bleaching across that entire region. And so this isn't consistent with loss of a ligand. This would be consistent with the coordination strength getting, the coordination getting stronger between the ligand and the metal. Which was a little perplexing at first until we went back to Salmon's work. And he did a number of studies with cyclohexene, and again, didn't have any direct evidence to support this, but proposed that possibly cyclohexene follows a completely different mechanism, and that it actually goes through a monocoordinated intermediate, and photoexcitation results in cis-trans isomerization of the cyclohexene. And then the trans cyclohexene would bind to the copper triflate, and this would be the reactive species that reacts with another molecule of cyclohexene that it encounters in solution. And this is important because trans cyclohexene is known to coordinate metals much stronger than cis cyclohexene because of the additional ring strain in the trans isomer. So coordination upon the metal relieves that ring strain, and so you get much stronger interaction. So that would be consistent with the fact that we see this bleaching in the 1s-4p. Now, it's consistent with this model, but it's certainly not direct evidence in support of that. So we'd certainly need more to really be able to know for sure that this is what's happening. So updating our summary again, with copper triflate, we've now shown that the photo dissociation appears to occur on the 300 picosecond time scale, followed by a slow equilibration step that we don't really know how to assign that. That has a time constant of 5 microseconds. But we do know for sure that within our 50 microsecond observation window, we don't recover the steady state absorption, X-ray absorption spectrum. And so whatever transient species we form is very, very long-lived. For the copper plus norbornene, we now see that it appears that the product formation, which is concomitant with dissociation, is also occurring on the few microsecond time scale. And for copper plus cyclohexene, we don't see any evidence of a charge transfer like we saw with norbornene. We don't see any evidence of photodissociation like we saw with both. And if anything, we see some very preliminary evidence for formation of the trans cyclohexene intermediate proposed by Salmon. I think this is before I move on to the optical work, this is probably a good time for the second break.
All right, very good. And thank you for sharing us. I think a lot of this work is before publication, is that right?
Yes, hopefully not too long before publication,
yes,
we'll see.
It's wonderful. First, kind of a very general question. Of course, you were a bit photon flux limited. You weren't able to do the extended XAFs, and your different XANES has some noise. Can you give us a little bit of background on the limitations in count rate and how that could be improved on in the future, either at different facilities or by something they could change at APS?
Yeah, I think, so I should say it looks like we were photon starved based on the signal to noise, but actually our signal was our actual X-ray absorption signal, the fluorescence signal that we measured was fantastic. The signal to noise limitation that we ran into was, I believe, some combination of just very weak absorption of the complex at 267 nanometers, combined with competition with formation of solvate electrons, which I'll talk about in a second, and possibly just fairly small changes to the XANES spectrum in general. We did try measuring this with higher concentrations of copper, and we did everything we could to improve the photon count rates, but nothing really seemed to improve our difference signal, which was always in the range of 0.1 to 0.2%.
Sure, but all the same, if you had 100 times photons, 100 times more photons.
Sure.
I guess where I was going is I didn't remember at that beamline how large an array of avalanche photodiodes they had. And, if they could wallpaper a part of the room, so to speak, with APD units.
Sure,
could you?
Yeah.
Uh-huh.
Yeah, the way this is set up is just one APD on either side at 90 degrees relative to the incident beam.
Okay, so there's a lot of room available with effort.
Absolutely, yeah, absolutely.
Okay. Is there any, go ahead, sorry.
Oh, I was just going to say well, never mind.
Okay. Is there, what would be the sort of cost benefit analysis of doing this kind of experiment at an XFEL? Would it be a clear win, or are the timescales wrong?
I think so. I think that will become clear in a second when I talk about the ultrafast dynamics that we got from Optical. But I don't know that in terms of dynamics, being able to do femtosecond resolved experiments, do this as a femtosecond resolved experiment is that crucial. Okay. Yeah, of course you could benefit from flux there. I think the real thing that was going to make a difference, and this was something that we had expected to do last a year ago at this point, basically, but obviously that didn't happen, was to redo this experiment with a higher repetition rate laser, so we could just get much better signal averaging, because if you look at our different spectra where I could bin a dozen spectra together to get a 1 microsecond snapshot, those look fine. It's just when we only have one X-ray pulse per laser pulse at 100 picoseconds, it starts to look really bad. So increasing the laser rep rate, I think, is going to make the biggest difference.
Okay, very good. Thomas Rossi, you have a question?
Yes, thank you. I have two actually. So my first question is, what laser fluence do you work with for these measurements?
Yeah, so our fluence is fairly weak since we are running at 10 kilohertz with third harmonic, and so I'm trying to do the calculation on the top of my head. I can tell you that we have about 75 microjoules per pulse, and we keep our spot size fairly defocused so that we fully cover our X-ray pulse, so in a spot size of about 2 millimeters.
Okay, so that's very low, yes. And so
It's very low.
you don't think that you can have the solvent heating on these time scales that could possibly give you a transient, actually, because the local structure of your molecule would basically change because the lattice temperature is different.
Yeah. So we did a temperature calculation, and I got, I want to say like 0.15 Kelvin was going to be the temperature change. Also, you know, that at least as soon as we're looking at microsecond dynamics, that's no longer really going to be operative. But it certainly was something we were worried about at earlier delay times. Yeah.
Okay. Thanks.
Mm-hmm.
Okay, Yang Ha, do you have a question?
Yeah, I'm curious about, you mentioned about the coordination number change from the XANES, but can you clarify on the geometry of the copper side, like whether it's a tetrahedral or a square planar? So the reason I'm asking is because copper 1 and the copper 2 may favor different geometric structure. So that might be the reason when you have a more steric, like a double bond, so it cannot favor like one structure versus the other.
Yeah. So for the olefin complex, we expect that to be a linear 2-coordinate system. So THF is a really bad ligand for copper 1. So so the copper alone, we think, you know, is of course solvated by THF, but is still strongly interacting with it with a triflate counterion. So we don't really have a good picture for what the and there's no you know, there's no literature in terms of what this what that particular system would look like. So we don't really have a good idea of what that would look like. But the copper-norbornene complex we expect to be linear 2-coordinate with, you know, perhaps some interaction with THF molecules. I would expect it to be very challenging to distinguish between coordination number if we were comparing that for the copper 1 and the copper 2 species directly, of course. But since we see this reverse electron transfer happen before we see a change in the or a rise in the amplitude of the 1s to 4p peaks, it does seem like we're comparing 2 different copper 1 species. So that makes me feel better about doing that type of analysis.
Okay, cool.
Very good. You should continue, please.
Okay, so so as I alluded to, we did all these measurements in August of 2019, and we're very excited to go back and fill in all the gaps and do this with a higher repetition rate laser and all that sort of great stuff last year, which of course never happened. Hopefully, fingers crossed, we'll get to do it this summer. That's what we're hoping for. But in the meantime, we did what we could. So we went back to our lab and did optical transient absorption measurements. And one good thing about doing the optical measurements, but with the X-rays, we're of course exclusively sensitive to the copper. With the optical measurements, we're sensitive to potentially everything. But in this particular case, it's essentially a selective probe of copper 2. Because the copper 1 species itself, the solvent, the ligand, the copper ligand complex, all of those have no absorption in the visible. And so as soon as we expect from the XTA results, form this transient copper 2 species, now we'll suddenly have a ligand field transition accessible in the visible. And so we'd expect our optical transient absorption to selectively report on copper 2 species. The downside to that is our copper 1 triflate is only about 98% copper 1. There's some contamination with copper 2 that gives the solution a bit of a tint. That's not such a problem for the X-ray transient absorption where, you know, we're 98% copper 1, but now if we're not measuring the copper 1 at all, it is going to be a challenge for the optical transient absorption. We also have to contend with the fact that since we're using UV illumination, we are forming solvated electrons. But by comparing the optical and the XTA, we can take advantage of the specificity of each and to overcome the limitations of the other. So, first we did femtosecond measurements with the copper-1-norbornene species, and we see this, quick spike with a lifetime of about a picosecond. We're not interested in trying to analyze that in much detail because that's going to be some awful combination of coherent artifact, thermalization, solvate electron, which relaxes in a picosecond. So we're not going to try to say too much about that. But what we do see is this very clear, slow rise that occurs anywhere that we take a trace through our transient absorption spectrum. And you can see it here in the TA spectra that at half a picosecond, we're still nowhere close to our maximum, which we don't reach until about 20 picoseconds. The spectrum continues to grow until we get to about 20 picoseconds, and then it doesn't really change on the nanosecond timescale. For these measurements, we can only go out to 2 nanoseconds. So we fit this and did decay associated analysis, and we get these 2 decay associated components. The blue one has a lifetime of 4.2 picoseconds, which accounts for the slow rise here. And then this red component persists for the duration of the experiment and doesn't really appear to decay. So since we see this negative signal here, that could be where we don't have ground state absorption. This could be stimulated emission from the singlet MLCT, or it could simply be the fact that the triplet MLCT has stronger absorption here, and so we get something that looks like a negative component as that excited state absorption magnitude just continues to rise. Either way, this 4.2 picosecond component that we get is fully consistent with what you would expect for intersystem crossing in copper MLCT state, so we feel fairly comfortable making that assignment. We definitely see immediately upon excitation a clear copper-2 signal in our optical transient absorption spectrum. So this answers the question of, we saw an XTA within 100 picoseconds we form copper-2, but is that necessarily the first thing we form? And so this shows that that is indeed the case. But it has the same limitation in terms of time window, 2 nanoseconds, as our XTA kinetic trace. So we still don't know the lifetime of the MLCT state. So we did nanosecond optical transient absorption, or flash photolysis. This becomes has some challenges now from the solvate electron because the quenching of the solvate electron occurs on the microsecond timescale. But since cyclohexene, if you recall, doesn't appear to go through a charge transfer state from the XTA, we measured that as well and saw that it looks essentially the same in regions of the spectrum where you don't have excited state absorption with norbornene, or with just copper alone. And so we can assume that this signal is coming from recovery of the solvate electron. We can subtract that from our copper plus norbornene signal and then just fit what's left, which is essentially the dynamics of this peak right here. And when we do that, we see a nice exponential decay with a 24 nanosecond time constant, and then a bit of 100 nanosecond component that might be just an artifact of the subtraction. So I don't really feel comfortable assigning it to anything conclusive at this point, and then nothing else after that. But this is nice because it allowed us to pin down the reverse electron transfer time constant instead of just saying somewhere between 2 and 150 nanoseconds. Now we know it's 24 nanoseconds. So we can add to our running summary of copper triplet with norbornene based on what we know from optical experiments. We initially populate the singlet MLCT state, and then intersystem crossing is occurring on the 4.2 picosecond timescale, followed by reverse electron transfer in 24 nanoseconds. maybe we're seeing evidence of a carbon-carbon bond formation in 100 nanoseconds. I'm not so sure about that because we wouldn't expect to be able to really see dynamics with the copper-1 intermediate in the visible. If we could do our nanosecond transient absorption experiments with a UV probe, then we might be able to see that, but I'm skeptical that that's anything more than just an artifact of our subtraction. And then finally, what we know about long time scales from our X-ray transient absorption in terms of product dissociation. So to sort of wrap this up, these are a small handful of the possible mechanisms that I mentioned at the beginning. At this point, we know that the mechanism proceeds through an initial copper-2 excited state, followed by a reverse electron transfer to a copper-1 intermediate. So we can eliminate all the mechanisms that don't invoke a copper-2 state because we are indeed forming a copper-2 state. However, there's still many questions left to be answered. So for example, are we simply forming the copper-2 state and then upon reverse electron transfer forming the ligand triplet diradical, and so in a sense just sensitizing that ligand triplet state? In that case, is copper essentially just acting as a triplet sensitizer plus a template, as distinct from a true intermolecular triplet sensitizer? We also don't know if our intermediate is linear or metallocycle. We're hoping when we can get better signal to noise to do XAFs that this might become more apparent. And now, especially that we know from optical transient absorption exactly what times to look for these species, we'll hopefully be able to pin that down the next time we do the X-ray transient absorption. So then other questions that we need to address, like with the cyclohexene, is there truly an entirely different mechanism that's operative for substrates that are isomerizable like cyclohexene compared to norbornene, which cannot undergo cis-trans isomerization because of that bridging methylene group? What's truly happening on the microsecond timescale and beyond in terms of these ligand dynamics? And furthermore, what about dienes? And so this is something that we're just beginning to look into, both rigid and floppy dienes. How do these dynamics compare? Is it, you know, I would have expected it to look very similar to norbornene, but I also would have expected cyclohexene to look very similar to norbornene. It looked entirely different. So we're excited to try that out as well. And we're just beginning to do the optical experiments on that now. And then finally, there are LMCT states at shorter wavelengths that it might be possible to access. And if that's the case, can we see an entirely different reaction mechanism that proceeds through those? So with that, I'd like to thank everyone in my group, specifically Callie, Gethmany, and Missy. So this is Callie, Gethmany, and Missy here, who ran these experiments at the APS with me in August 2019. And then Gethmany has since taken over and done the nanosecond transient absorption. Callie did the femtosecond transient absorption measurements here. I'd like to thank our collaborators at Rhode Island College who participated in this experiment at the APS with us, and of course the fantastic Beamline staff at 11IDD at the APS, without whom none of this would have been possible. I'd like to thank funding from both ACS PRF and NSF for supporting this work, Argonne for housing us for an entire summer, and I'll leave you with this photo of us at 2 or 3 a.m. during this experiment while I take any other questions.
Really great stuff. Thank you. There are indeed a few questions. Joshua Vera-Weiss, you had a question? Okay. Yulia Pushkar, you had a question?
Nice stuff. So my question is, can you do any time result vibrational spectroscopy to kind of follow the bonds, chemical bonds?
Yeah, I think that would be a really nice thing to do. I worry that we'd run into the same limitation that we would for ligand K-edge measurements, where since we have to do this in a huge excess of ligand, would we be able to see, you know, a small change in a small population of ligand that's actually coordinated to the copper? It's certainly something that would, I mean, it would be incredibly useful in terms of actually providing direct evidence of these, you know, putative intermediates, but we haven't tried doing it yet, mostly just because I am skeptical we'd be able to get sufficient signal to noise.
What prevents you from reversing? So what prevents you from using 1-to-1 or even, you know, excess copper?
So so if we do it at lower concentration of ligand, then we're going to have a mixture of uncoordinated copper, monocoordinated, and biscoordinated, and only the biscoordinated is reactive. And so suddenly, if we have to, if now we have to worry about thinking about the transient species that we would see upon excitation of the monocoordinated and the biscoordinated, I think that could be challenging. I mean, that's a good point, because the uncoordinated, we don't have to worry about that like we would in the XTA, since, you know, we're looking at the ligand.
But do you know on which time scale your product builds up? So what is really kind of, what is the time scale of those bonds formation?
Yeah, so we think that that's on the time scale of a few microseconds. So it certainly should be doable to do those measurements. It's just a question of how will our signal from the reaction versus the transient vibrational spectrum of the excited monocoordinated copper species compare.
Okay. Thank you.
But it's a great idea, and I think the fact that we don't have to worry about the uncoordinated copper would make that simpler in some regard.
Okay, Josh, you're there. Joshua, you're available now, yes?
Yes.
Great.
So I noted, you know, so for like iron tris-BP, the singlet MLCT to triplet MLCT happens in like 30 femtoseconds. So I was surprised that for the copper, it's 100 times slower. Is there a reason for that? And I'm sure this isn't just like a geometry change. Like, I know, like a lot of these copper 2 chromophores, there's like a square planar to tetrahedral geometry change in a couple picoseconds.
Yeah. So for again, I think a lot of our limitation in terms of assigning these things is from the fact that we don't have a good picture of exactly what the coordination geometry is. But thinking that we have that we're starting from a linear species, there's less of a I guess I get less of an argument to be made for a Jan-Teller type distortion there, but I believe the intersystem crossing rates for even those copper species are also in the few picosecond time scale. I think they're on the same time scale as the distortion, I believe.
Are the two spins more coupled, or is there, do you know any, is there physical, I'm sure there must be, I just don't know what it is.
I mean, I'm thinking back to this one paper from Gier where she was directly comparing spin orbit coupling or looking at spin orbit coupling as a function of ligand geometry, and showing that the intersystem crossing rate itself varies with the initial geometry. But I can't remember exactly what the argument was.
Okay. Thanks.